Good morning, all of you. My name is Pramod Kumar, a lecturer in computer applications from SCNR Government Degree College, Prodhutur. Today, I am going to discuss about binary search tree from data structure. A binary search tree, hierarchical data structure with a single reference to root node. From this example, we can identify that 25 is a root node. Each node has at most 2 child nodes. Every node should have at most 2 child nodes. These are the 2 children. This is the left child and this is the right child. And here 50 is the left child, 15 is the left child and 50 is the right child. Nodes are organized by the binary search tree property. To construct a binary search tree, we have to follow some rules and regulations. The first one is every node is ordered by some key data field, and here the data elements are to be called as keys. Here 25 is a key, 15, 10, 4 and so on. These are all the keys. For every node in the tree, its key is greater than its left child key and less than its right child key. This is the main property for binary search tree. Every node in the tree is greater than its left child node. This is the left child and this is the right child. And here the right children are less than the left children are less than the right children. Here 25 is the root node and this is called left subtree and this is called right subtree. From this example, we can identify that, and the right child 15 is less than the 25, left child 15 is less than the 25, and right child 50 is less than the 25, greater than the 25. And this property continues at every level. And here we have some binary search terminology. The root. Every binary search tree has its own root. Here the 25 identified as the root node. And child node has exactly one parent node, and this is the condition. And every child within the binary search tree must have only one parent node. That means 15 has 25 as a parent, and 50 has 25 as a parent. When you observe this diagram, every child has only one parent. This is the condition in binary search tree. A leaf node has no child nodes. From this example, 4, 12, 18, 24, 31, 44, 66, 19, these are all the leaf nodes. That means when a node doesn't have any children, then that node can be called as leaf node. From this example, we can identify the 4, 12, 18, 24, 31, 44, 66, 19 are the leaf nodes. And here, as a fourth point, every node in the binary search tree is a subtree of the binary search tree rooted at that node. Every node is subtree. From this given diagram, this total left tree is a subtree, and this total right tree is a subtree. And for the left tree, the 15 is a root node. From the right tree, 50 is a root node. And the second one is how to implement binary search tree. From this example, we can write some abstract data type. This is the ADT to construct binary search tree. And here we have left and right. The left means is the pointer pointing the left subtree, and the right means pointing the right subtree. Here data, where we place element within the field, that is called data, and this is called the next recursion, and we can form the next subtrees. The left refers to the left child and right refers to the right child. Next, operations on binary search tree. Mainly we have four operations. First one is how to create binary search tree, and second one is find a node in binary search tree using some key element, and third one is add a node to the binary search tree, and fourth one is traversing. Traversing means we have to move from every node, from one node to another node. Thus traverse means visiting every node in the binary search tree. And this is some pictorial representation of the binary search tree ADT. This is the root node. This is the pictorial representation of the root node. Here data field contains some key element that is the key. This is the root node. And here the left pointer points to the left subtree and right pointer points to the right subtree. And the first operation, find a node into the binary search tree. And how to find a given node from the binary search tree? So we have to move from the starting node. Start at the root node as a current node. If the search key value matches the current node's key, then found a match. If the search key value is greater than the current nodes, if the current node has right child, search right, else no matching node in the right tree. If the search key is less than the current nodes, if the current node has a left child, search left, else no matching node in the tree. Let us see one example. So we have to search from this example, we have to search the number 45. This is the key node to be found. We have to start our search from the root node. Here is the 25 is the root node, and the node to be found is 45. So we have to compare the 45 with the 25. When compare the 45 with the 25, the 45 is greater than the 25, so we have to move to the right subtree. Because the binary search tree contains the key elements which are less than the root node in the left subtree, and the binary search tree contains the key elements which are greater than the root node in the right subtree. Based on this property, to search the 45, we have to check right subtree, because the 45 is greater than 25, so the 45 will be within the right subtree. So when we move to the right subtree, here the 50 is as the root node. When compared the 45 with the 50, the 45 is lesser than the 50, so we have to move to the left subtree. Again we have 35 as a root node, and when compared the 45 with the 35, the 45 is greater than 35, so we have to move to the right subtree. But when we compare the 45 with this key element, here we have only 44, and this is the leaf node because it doesn't have any children. So here we could not find any 45 value. So that means the requested element 45 is not found within the binary search tree. This is the simple example. And next, how to insert a binary search tree. And the same process, what we did to find a given element in the binary search tree. So we have to do the same thing to insert a new element within the binary search tree. So we have to find out the root node, the which element that we want to be inserted to the binary search tree should be compared with the root node, and if the newly insert node is greater than the root node, that should be inserted within the left subtree. If it is less than the root node, it should be inserted in the left subtree. So the process continues. For example, here we have taken the key element 60 to be inserted within the binary search tree. When we compared 60 with the 25, the 60 is greater than 25, so we have to move to the right subtree, and the process continues. 60 is greater than 50, so we have to move to the right subtree, and 60 is less than 70, we have to move to the left subtree, and 60 is less than 66, so we have to move to the right side one. So we have to insert the 60 as a right child of the 66. And the traversing concepts already we have discussed in the classroom. We have three main traversing techniques: pre-order traversing and in-order traversal, post-order traversal. Pre-order traversal means we have to traverse the root node first. In-order traversal means we have to traverse the left subtree second one is the root node, and the third one is right subtree. Post order traverse means we have to search the left subtree and then right subtree. The lastly we have to traverse the root node. This is the traversal code, simple algorithm, and this is one example and how to traverse our binary search tree, and these are some examples and how to traverse the binary search tree. And this is all about binary search tree. If you have any doubts, please ask me through the WhatsApp. You can post your doubts in WhatsApp and I'll clarify directly through the WhatsApp. Thank you very much, all of you.